Well, thanks a lot. This is going to be a very brief version of this topic, but if you want to see more, in a half an hour, I'm running over to SETI and giving an hour-long version of the same thing. So, which one you want to see? Do you want to see less of me or more of me? My guess is less, but that's the... Look, he's got to put up my talk. What can I do? I can't do anything yet. Okay, that's the last slide. Thank you very much. I'll be here all week. Okay, well, so this is going to be a review of some of the things that we're thinking about in terms of the bombardment history of the moon, when my views have been changing in this by quite a bit. So I'm going to try to present some new things here that maybe you haven't seen before. So let me jump to the first slide. And so I was trying to think of a way to express how far I've come in my thinking on this. And I was watching an old movie, and I came across this great quote from Artemus Ward, who was an American humor writer, who was actually one of the favorites of Abraham Lincoln. And he's got some great quotes. It's worth looking up. But essentially, one of the things he said is it ain't so much the things that we don't know that get us into trouble. It's the things that we do know that just ain't so. Okay? And to some degree, this expresses how much I've struggled with this, because I keep thinking I know things, and it turns out I may not. So some of the things I think that are common knowns about the late heaven bombardment that may be questionable is the following. First of all, many people argue it's a spike. And what they mean by that is it starts about 3.9 billion years ago, and it lasts maybe on the order of about 200 million years or so. Okay? The second thing, that all of the lunar basins are in that spike. Or, depending on which camp you believe, none of the basins are in the spike. But either way, it's an all or nothing game. Okay? There's no room for in between. Okay? The third thing, that everyone thinks that the late heaven bombardment ended across the solar system on every single world. It ended just about the time that the Oriental Basin formed, about 3.7 billion years ago. And finally, that essentially all large-scale late heaven bombardment impact signatures have been erased for the Earth. There's nothing left. And I'm going to argue in this talk that actually all four of these are probably wrong at some level. Okay, so let's jump forward here, if I can. Go forward. There we go, okay. I'm sorry, I gotta... Okay, so to explain the late heaven bombardment, I have to... There, let's try this one again. This is slow. Okay, so to explain the late heaven bombardment, I have to give you some context for things. And so one of the things I have to explain is how would we get a late heaven bombardment? Well, the best developed model we have of this to date is called the Nice model. In the Nice model, the giant planets form on circular orbits in a much different configuration than they have today. And they stay this way for hundreds of millions of years. And then an instability takes place, basically because Jupiter and Saturn enter into a resonance with one another. Don't worry about all the dynamics, but essentially what happens is that this destabilizes the system. Uranus and Neptune migrate through the disk, and they cause this big comet disk to go flying all over the place. And so this is a possible source of projectiles for the moon. Okay, so this is one thing that happens. Okay, so let's go forward from there. So what happens at this point is after some delay, you have this very narrow spike of comets, according to the classical model of this, which is by Gomez et al. In 2005. So the comets last for a few tens of millions of years. And then what happens, because the giant planets are moving around, all their resonances are moving around, and they destabilize parts of the asteroid belt. And so then you get impacts from asteroids over the next 200 million years or so. And this fits our classical model very well, and this is why everyone seemed to like this model. Okay? But there was a problem that didn't become really apparent to me for quite some time. But if you read the paper, in order to get everything to work in terms of the mass of hitting the moon, they need that asteroid belt to lose about 20 times its current population. So that means it loses 95%. And it turns out that's a lot. Having the asteroid belt have this much mass for hundreds of millions of years is not so easy. Okay? But that's only part of the problem. Okay? Let me jump forward here. Okay, there's a delay here. All right, so new models that have been done. I'm not going to show you all this. I don't have time. Come to my talk in a little bit. I'll tell you more about this. But David Minton and Renu Malhotra and Alessandro Morbidelli have been following up, looking at dynamically what happens to the asteroid belt when the giant planets move around. And they're finding that the best they can do is remove maybe about a quarter to about a half of the mass from the asteroid belt. And that's only enough to produce about 2 or 3 lunar basins. And some other work that Bob Strom and other groups have done suggested that comets clearly can't make up this difference. And so all of a sudden we have a problem from a dynamical perspective. We need more impacts over a longer interval to explain many of the basins we have in the moon, and our major sources are going away. They have major problems. So what can we do? Okay, well, something to keep in mind, so let's not throw everything out with the Nice model, because the Nice model can do a lot of interesting things, but here's something to consider. Today the asteroid belt ends at about 2.1 AU, and the reason it ends there is because there's a secular resonance called the nu 6 that actually defines the edge of the asteroid belt. Things that get in there get pushed onto planet-crossing orbits. This is where we get our near-Earth objects from. But before the giant planets took on a new configuration, that resonance was not there. And there was simply no natural stopping point for the asteroid belt. So it very likely just kept going, all the way down to a Mars-crossing orbit. And so I'm calling this hypothesized extension of the asteroid belt the E-belt. So the E stands for extension. The E stands because population is now largely extinct. And there's also, I can keep going on E's, but we'll go from there. But this population does a lot of neat things that may solve some of our problems in terms of dealing with the late bombardment in the inner solar system. Okay, so here's a picture of the inner solar system to give you some context for this. Here's some major axis, here's eccentricity, here's inclination. All these bodies here are the small little asteroids we have in the inner solar system. So here are some of the boundaries we have. This is the nu 6 secular resonance right here. So you can see how that truncates the asteroid belt. Over in eccentricity, we have Mars-crossing orbits. And you'll notice that there's this little interesting population called the Hungaria asteroids here. This is this little green box here. They're actually the closest small body reservoir we still have to the terrestrial planet region. But there's not much stuff there. Okay, the largest object there today is about 10 kilometers. And so you can really say a lot about what it used to be just by looking at it from today. But interestingly enough, it is filled with a lot of something exotic type asteroids, which actually are an interesting part of our story. But I'll talk about that in a little bit. Okay, so the question is, what are these Hungarias telling us about the solar system in general and how it's evolved? So as a hypothesis, we thought, let's try to do this. Let's actually fill in the asteroid belt according to what we think is going on here. So we put test bodies in this region and over here, and we tried to model it before the giant planets, or before the Nice model took place, and afterwards. We first want to see if the orbits are stable, then we want to see what happens when all the resonances are put into their current place. Okay, so here's a movie of this. Okay, so you're going to see for the first part of this, for several hundreds of millions of years, you see this population loses maybe on the order of about 10% of its mass, or 15% or so, but most of the mass is still there. And then when the Nice model takes place, this population goes away, and it goes away over hundreds of millions of years. So it goes away over a very long time scale. So what's interesting about this is as follows. First of all, these guys are about 10 times more likely than your typical main belt asteroid to hit the Earth or hit the Moon, so you get much more bang for your buck. You don't need a lot of mass to produce a lot of big impacts. You also get some interesting effects in terms of impact velocities. The velocities hitting the Earth and the Moon are actually double what they were before. There's actually crater evidence for this that I don't have time to show today. But we also get some very interesting impact profiles, and I'm going to show that, and that's sort of the punchline for this talk. Okay, so first of all, one of the neat things about this is you'll notice as these objects evolve, they get into this little region where the green box is. This is a region that's just quasi-stable. It's surrounded by resonance, but actually in there are very few things that can pull these guys out. And so this model actually has a way to make Hungarias. So the E-belt may actually make these guys. And this is really nice, because first of all, this is sort of a test, but also we can use this in some fashion to use the existing Hungaria population to estimate back what the original population was like. So we've actually modeled this for our population for 4 billion years, and whenever we get statistics get too low, we clone things and keep going. And what we find is this population has dropped by about 3 orders of magnitude. So if we go from the current Hungarias and we go backwards in time and we say, well, how much stuff was here? It turns out the amount of stuff was there is about just what essentially has the same population density that the asteroid belt had at the same time. So this is a nice consistency check. Everything seems to be working together. So if we then go forward and say, well, how many basins should we get on the Moon from that? It turns out this population should produce about 9 to 10 lunar basins. And about 2 or 3 of them should probably be Imbrium or Oriental size. So that's not all the basins on the Moon, but it's some of them. Okay? So if you combine that with what we expect to get from the asteroid belt, together we're getting about 12 basins on the Moon. And so that means that if this is right, the asteroidal component to the late heaven bombardment should start somewhere around the time of Nectaris or so. And many of these basins have to come from some other process, maybe late accretion or something else that's going on here. Okay, so how can we prove this? Well, there's a number of different ways. I don't have time to talk about all the ways. One, as a consistency check, what we did is we took how many craters we would expect to be on Nectaris Basin, which is sort of the beginning of what we're saying the late heaven bombardment is, or close to the beginning. This blue line is what we get from the asteroid belt. The red is what we get from the E-belt, and the green is combined. And you can see it does a pretty good, nice job of matching the craters we see there. So I don't think that's conclusive of anything, but it's good that it works. Okay, this is a nice consistency check. Okay. The second thing we could do is this. We know the very last basin to form on the moon is Oriental, and it formed about 3.7 to 3.8 billion years ago. And we're predicting from the E-belt that we get about 9 basins. So this is cumulative number of E-belt impactors. This is time after the late heaven bombardment starts. And so we can actually scale everything for this fashion. Okay. So if we do that, we can make a prediction as to when the late heaven bombardment had to start. And if this is right, the late heaven bombardment doesn't start at 3.9 or 4.0 as what people think, but it probably starts somewhere around 4.1, 4.2 billion years ago. Okay. And that actually seems very consistent. Okay. Very consistent with many of the different new sample evidence we're getting from asteroids, from Martian meteorites, and from lots of different lunar samples. So this actually seems to fit really nicely as well. And so this would also mean it's not really a spike in a sense, because the late heaven bombardment in terms of basins is lasting almost 400 million years in the moon. So that's a long time. But there's more things we can pull into this. First of all, people tend to think, well, when the basins end on the moon, that's it for the late heaven bombardment. But there's still a tail that goes on here. So what we did is we looked at craters that were, let's say I'm going to call them KT sized. These are objects that maybe were 160, 170, 180 kilometers or larger. They actually form after Oriental, so we scaled up our model to take into account for that. So we're going to look at this time period there. This is what we call the late Imbrian period. It goes from about 3.2 to 3.7. And over here we have what's called the Eratosthenian time. And that goes from about 3.2 to maybe about 1 or 1.1 billion years ago or so. The observations predict we have about 3 craters in here, and about 1 crater is on the moon formed over that time. That's just about what our model predicts. So this nice long tail seems to be verified by other big-sized craters. But here's the interesting part. Look at all this stuff over here on the Earth. Okay, so what could be going on there? So hopefully this jumps ahead. So when the Earth gets hit by a big impactor, and let's say KT sized, it does some interesting things. It vaporizes a lot of material and makes a big crater. But it also does is it launches and ejects molten silicates all across the planet. This stuff goes into orbit, it cools, forms these little sand-sized things, and they rain back down on the Earth. They're called impact spherules. This is what Barb Cohen was mentioning today. Okay, so what this means is you get a global layer which can be millimeters to centimeters thick of representing a very large impact on the Earth. And so if you have terrains that are still preserved from old times on the Earth, you can say something about the impact record, even if the crater is gone long ago. And the people who are working on this are Bruce Simonson and Don Lowe, who's here in Stanford, and Byerly and Frank Kite's done some work on this. And so we can use this to our advantage. So if we take a look at the Earth, and we look at the terrains that these guys have investigated, what they find is this, okay, is that these boxes represent terrains in the Archean where they've actually looked for impact spheral beds, and they think they have I won't say complete a record, but they think they've found many of the major impact spheral beds. And over here, our model's predicting about 9. So far, we predict about 7, but Don Lowe told me in an email that he thinks this number is actually about 9 or 10. They have some things they haven't published yet. Over here, we're predicting 3. Bruce Simonson suggests there's about 4 there. Here we have 2, and there's 2 here. And so you can see this line works really well. Okay, and I'm just about out of time. So the punchline of all this, okay, is that this is right. The late heaven bombardment does not end at 3.8 billion years on the Earth. It makes about 15 basins during the Archean time of the Earth, from about 3.7 to 2.5 billion years. And there's about 60 more KT events that happen from about 3.7 to 1.7. So if this is right, craters like Fredefort and Sudbury may be the very end of the late heaven bombardment on the Earth. And I'm out of time, so I think I'll stop there. Thanks.
We have plenty of time for questions because we think we're going to cancel the next talk. So, quick question for Bill. Even quicker question for Bill. One question. Alberto.
Yeah, Bill, you think that this email